Assis au banc, pas loin de la porte. Je regarde danser les Black Label sur une vieille tonne de Nation. J'y pense justement même pas. Chaud comme un spot dans les culottes. Les carrosseries toujours jouées. J'ai une gueule pour diviser. J'y pense justement même. Le charmant étudiant était m'ont invité à leur cégep pour aller jouer de la belle musique. Zézé, pas pour faire mon grand comme une plate. Une plate qui se passe 50 pas. Qui flotte à droite, qui flush à gauche. Je veux pitcher stage avec mon Dieu, j'y pense à plus partout. C'est une acclame qui se t'assoit. Je suis content d'être du pouvoir. Je vous remercie pour la grosse pierre. J'ai eu du fun à jongler.
Yep, indeed, Jonquière. Jonquière by Plume La Traverse. Since it's still early, let's continue on with Rideau by the same artist.
Mettez vos lunettes sur votre banc. Assoyez-vous bien dimanche. Votre joint dans l'anus, votre pied entre les dents. Ça n'en prend pas plus un balance les enfants pour faire un gros show. On va essayer de faire votre symphonie. Et ceux qui sont en tabarnak, ils verront nos ailes à l'entraque. On est bien ouvert à vos commentaires si vous payez le cognac. Si vous payez le cognac. Coulez votre belle-mère dans le silence. Faites-y visiter le Saint-Laurent. Poignez votre voisin d'arranger dans l'avant d'un ami qui a le coup de poing approché jusqu'à temps qu'il fasse un bon show. Après, à ce chemin, faites ça comme il faut. Et ceux qui sont en tabarnak, ils viendront nous voir à l'entraque. On est bien ouvert à vos commentaires si vous payez le cognac. Si vous payez le cognac. Oh yeah! bon, même si vous êtes sourd. On n'a peut-être pas de nom, mais on se bat tous les jours pour faire un bon show. Et ceux qui sont en tabarnak, ils viennent nous voir à l'entraque. On est bien ouvert à vos commentaires si vous payez le panier. Si vous payez. Hey, gagnant. Wow, wow, wow.
We have time for one more. Let's do it.
Asparpe ma terre et bâtie, à Coureuil, la rue Sainte-Catherine. Qui ça? Bon bébé. Bon bébé. Bon bébé. Bon bébé. C'est la coqueluche des grands drivers, à pas fureur avec ses bottines. Qui ça? Bon bébé. Bon bébé. Bon bébé. Bon bébé. Son père travaille dans une usine, sa mère accouche dans la cuisine. Qui ça? Bon bébé. Bon bébé. Bon bébé. Bon bébé. Eh ben pogné sa nicotine, pis eh ben chum avec ma voisine. Qui ça? Bon bébé. Bon bébé. Bon bébé. Bon bébé. Bon bébé, yeah. Danse de rock chrome et full pay comme une vraie super bobée. Qui ça?
All right. Now we're ready to work. Morning, everyone. How are we doing? So this morning's music brought to you by Plume La Traverse. All right. So, we've been looking at the definition of the derivative. And a few things, I think we noticed, or at least I pointed out, if S of t, right, immediate applications of the derivative, why do we want to study the derivative? If S of t is the position of a particle, a person, a car, the rate of change, right? Because that's what the derivative really is. The derivative measures the rate of change of something, right? Because it's the slope of the tangent line at one point, right? So it's oftentimes referred to as the instantaneous rate of change. And if S of t describes the position of something, then the rate of change of the position, or the derivative, is going to be the velocity. How fast something changes position, you understand that to be the velocity. Similarly, how fast the velocity changes, right? You're in a car, you're moving, and then you floor it. What happens? You change the velocity, you're accelerating. The rate of change of the velocity is the acceleration. So, immediate applications. Immediate applications, right? Sophia is asking, isn't it more like speed? The reason we use velocity is because you could be going forward or backwards. So a negative velocity, meaning you're going in reverse, if you will. So it allows for negative and positive. All right, so immediate applications of the derivative. Here we go. And as you know, we have been using these to find slope of the tangent line. Why don't we do one more example? We'll be drawing graphs, but not right now. So find the tangent line to this function at the point 1, -1. As we saw, the derivative gives you the slope of the tangent line, right? So if we call this f of x, the derivative gives you a rule for the slope of the tangent line. So this is x plus h squared minus 2x plus h minus x squared minus 2x, the whole thing over h. expand everything and cancel anything we can. The x squares cancel out. The 2x's cancel out. And then let's factor out an h from whatever remains. You're left with 2x plus h minus 2. Right, we only have these three terms. So factoring out an h from that. And now this allows us to cancel the h over h. And as h goes to 0, we just have this left. H is going to 0, so you see that you get 2x minus 2. This is a rule that gives us the derivative of this function at every point. Yes, thank you for that. I changed it because I didn't want us to take too much time. So I changed it from x cubed to x. Of course, you should not be doing that on an exam. I just didn't want to cube it. So Zuhair is asking, can't we simply differentiate? And we're going to address that today. But won't a graph sometimes have different derivatives at different points? Well, that's exactly right. I mean, we're saying that the derivative of x squared minus 2x is 2x minus 2. So you see that the slope of the tangent line differs at every single point, right? When x is 0, you have a slope of minus 2. When x is 1, you have a slope of 0, and so on and so on. Right, so here what we're saying, the derivative when x is 1 is 2 minus 2, which is 0. So the slope of the tangent line at x equals 1 is 0. So your tangent line, which has the form y equals mx plus b, here we've just worked out m to be 0. So as Jesse suggests, the slope will vary, but the derivative is the same function throughout the whole interval. Very nice. So when x is 0, I mean not when x is 0, but the slope is 0. So y equals b is the equation of your tangent line. And you know that it goes to the point 1 minus 1. So when x is 1, y is minus 1. So this is going through 1 minus 1. So when x is 1, y is minus 1. So b is minus 1. In other words, y equals minus 1 is the slope. Thank you. Is the equation of the tangent line. You can use, well, you know, I prefer this. This is my preferred way of describing a line. All right, but now as Zuhair and a lot of people have hinted at, we're going to move away from this limit definition into actual rules for differentiating. How did we know m was 0? But we found the derivative, and the derivative gives you the slope of the tangent line. So, yeah. So the derivative gives you the slope of the tangent line. So the slope is 0 here. So we're moving away from the definition of the derivative, the limit definition, into rules for differentiating. But keep in mind that you can always return back to this limit definition in case you need to. And in fact, all of the rules that we're going to give can be traced back, can be proven using the limit definition. So, first rule, let's call it a claim because we'll prove it. If f of x is a constant, the derivative is 0. The derivative of a constant is 0. Let's prove it. What is the derivative? Well, again, going back to the limit definition, it's the limit of f of x plus h minus f of x over h. You know, last time we essentially proved it, where we had, I think, 4 or something, but I mean, or maybe it was 0. But anyways, let's go over the proof again. What is f of x plus h? Everywhere you see an x in your function, you replace with x plus h, but there is no x. So f of x plus h is still c. F of x is c. And c minus c is 0. So the limit is 0. So the derivative of any constant is 0. It's a nice observation, right? And again, from a graph, if you have a constant function, it's not changing, right? Remember that the derivative measures the rate of change. This function doesn't change. The derivative is 0. Right? And, you know, Sophia's asking, well, don't we have 0 over 0 here? It's a valid question. We actually have 0 over h, and h is approaching 0, right? But it never actually reaches it. So for any value of h, you have 0 over a non-zero value, you have the 0 function. Right? 0 over h is 0, and the limit of 0 is 0. Exactly. As the Ash suggests, h is approaching 0, while c minus c is actually 0. So you have 0 over a non-zero number, you have the value 0. Another claim, and before claim, the derivative of the sum is the sum of the derivatives. Assuming f prime and g prime exist. So if f and g are differentiable functions, the sum is going to be differentiable as well. And the derivative of the sum is the sum of the derivatives. Again, we can prove this using the limit definition. Let's do it. This is just one line. Right? What is the derivative of the sum? Well, by definition, this is the limit as h goes to 0 of f of x plus h. So this function evaluated at x plus h minus this evaluated at x all over h. And I think you see what's going to happen, right? We're going to expand this. We're going to group the f's together, group the g's together, and notice, no, on the midterm you can just refer to the laws, unless I'm asking you to prove it. Right, so if you expand this and you group the f's together and you group the g's together, right, what do we have? F of x plus h minus f of x plus g of x plus h minus g of x, the whole thing over h. And now we're going to split it up into two pieces, because you know that you're allowed to do that in the case of the limits. Limit of a sum is the sum of the limits when both limits exist. So I can split that up as limit of this over h plus limit of this over h. Right? Does everybody see that? But let me not skip a step and let me rewrite it this way. Viewed as the sum of two fractions, if you will. Right? This over that, and this over that. And now the limit of the sum is the sum of the limits. You know that to be a property of limits. It's one of the limit laws. Assuming both limits exist. And finally, you recognize this as the definition of f prime. And you recognize this as the definition of g prime. And there we go. The derivative of a sum is the sum of the derivatives. Very nice. Let me, while we're here, let me introduce notation. for the derivative. Well, we already have this notation, but let me introduce another one. Well, perhaps a few more. F prime or df dx or dy dx of f of x, right? This is read the derivative of f of x, or sometimes just dx of f. I don't really use that very much, but some books do. There it is. So all of these things mean exactly the same thing. These are all notations for the derivative. Here we prove that the derivative of a sum was the sum of the derivatives. Let me give you a second claim. The derivative of c times a function, where c is a constant, so the derivative of c times a function is c times the derivative of a function. What does the x represent? Valid question. Instead, let's so first, before I move on from this, I'm not going to prove it, but you can prove it using the same idea as before. So left as an exercise. A very easy exercise. You should prove it using the limit definition. Using the limit definition and the fact that the limit of a product is the product of the limits, it's going to work out very nicely. So it's 1 or 2 lines. Some people were asking about the dx notation. Observe that when we define the definition, right, we saw that the definition was used to find the slope of the tangent line, and we approximated that by finding the slope of a line going through 2 points on the graph, a delta y over delta x argument. And then we investigated what happens as h goes to 0. And as h goes to 0, you're getting closer and closer to the actual slope of the tangent line. And notice how this delta y over delta x, if y is a function of x, right, this delta y over delta x becomes dy over dx. That's the idea behind this notation. Right, that's the idea behind the notation for the d business. So dy over dx can be thought of as, right, I mean here, right, if you recall what we were looking for the slope of the tangent line. We took 2 points on the line and looked at the behavior as h goes to 0. So we had the delta y over delta x business as the slope of this line, and then investigated what happened as h gets closer and closer to 0. And as h gets closer and closer to 0, the delta x becomes smaller and smaller, right? Closer and closer to 0. So That's why the derivative is often referred to as the instantaneous rate of change. It's the rate of change that's happening exactly at this point. So the d can be thought of as, well, I mean, they're sometimes referred to as infinitesimals, right? It's the infinitely small change happening there. As far as we're concerned, we're just treating it as notation. So it's not going to have any real meaning for us, but in different contexts, it could have some meaning. People are asking, isn't the derivative of a constant 0? But here it's a constant times a function. I'll invite you to prove it. Do we want to prove it? We probably should prove it. Let's prove it. It's quicker to prove it than to talk about how short the proof is. So let's prove it. The derivative of this, by definition, is this function evaluated at x plus h minus that function evaluated at x over h. Pull out a constant from the numerator. And the limit of a product is the product of the limits, assuming both limits exist. The limit of c is just c. This limit you recognize as the derivative, and there you have it. Convinced? Now let's talk about the derivative of powers of x. Why is c not divided by h? Well, I mean, you know what's happening there. If you have ca over b, this is the same as c times a over b. Right? You're not going to throw in another b there, because then you get b squared. Let's calculate the derivative of x. What is the derivative of x? It's x, by definition. I mean, I know what you're thinking. Didn't we say we were moving away from the definition, and yet we're always back there? Well, we're back here to prove certain properties, but we'll be moving away from the definition. We're really moving away from it. Right? Khan is asking, didn't we just say the derivative of c is 0, so why is the limit of c c? Well, I mean, it's two different things, right? We said the derivative of c is 0, and here it's the limit of c. Two different things. The x's cancel, and you're left with h over h, whose limit is just 1. Are we having trouble, Alexandra is having trouble? Is everybody else doing all right with the connection? Okay. Are there only 2 people here today? How are we doing? Let's calculate the derivative of x squared. Okay, excellent, thank you. Let's calculate. So what have we done here? We've calculated the derivative of x and we found it to be 1. Really, I mean, think of the, I've rubbed it off now, but think of the notation, right? The derivative of x, or dx by dx, we just said to be 1, right? I mean, it makes a lot of sense. That's just by looking at this as a fraction, which you should not, but because it's a derivative of x with respect to x, but it makes a lot of sense that this would be 1 just from the notation. Let's calculate the derivative of x squared using the limit definition. What is that? Right, and what am I doing? I'm trying to come up with a rule for the derivative of a power of x. Right, this is x to the 1. The derivative is just 1. The derivative of x squared, let's work it out here. Let's work that out. What is the derivative of x squared? This is x plus h all squared minus x squared over h. Expand this whole thing. See what happens. X squared 2xh plus h squared minus x squared over h. The x squares cancel out. Let's factor out an h from the remaining numerator. 2x plus h over h. The h's cancel out nicely, leaving us with a limit of, as people already knew, a limit of 2x. So let's recap. The derivative of x is 1. The derivative of x squared is 2x. Let's try one more derivative of a power of x. Let us consider square root of x, which is really x to the 1/2, right? Let's figure out that derivative, and then we'll ask the question, is there a general pattern arising? So by definition, this is the limit of square root of x plus h minus square root of x over h. We may have seen this limit before. How do we tackle it? As h goes to 0, this has the form 0 over 0. What are you going to do? Right? I mean, Jasmine has suggested a rule. Let's convince ourselves with the square root of x. Somebody's suggesting to multiply by the conjugate. Very nice. So root of x plus h plus root x over root of x plus h plus root x. Sorry about the lack of space here, but thank you all for the suggestion to multiply by 1, namely the conjugate over itself. Expand, distribute, see what happens, right? Numerator becomes x plus h minus x. Denominator will leave as a product. The x's cancel out nicely, leaving you with an h over h. So we can cancel that as well, leaving you with a 1 over this business. And as h goes to 0, it's easily seen to be 1 over 2 root x. So what have we done? The derivative, let's write that here, the derivative of x to the 1/2, this can be rewritten as 1/2 x to the negative 1/2, right? 1/2 x to the negative 1/2. So do we see what's happening? Right? This was x to the 1. This becomes 1, or 1 times x to the 0. The derivative of x squared becomes 2 times x to the 1. The derivative of x to the 1/2 becomes 1/2 x to the negative 1/2. Right? What's happening? The power comes down. The power comes down, and you subtract 1 from the power. Claim the derivative of x to the n, right? We're trying to describe, exactly, thank you. We're trying to describe the pattern we're observing here. The derivative of x to the n is n x to the n minus 1. Once again, you can prove this using the definition of the derivative. It's complicated if you don't have a specific value of n and you want to do it in general. So we're not going to bother, but that's the rule. The derivative of x to the n is n x to the n minus 1. So now let's make use of these rules, right? So we had this rule. We had the derivative of a constant is 0. We had the derivative of a sum is the sum of the derivatives. And we had the derivative of a constant times a function is c times the derivative of the function. You don't have to prove these laws anymore unless the question specifically asks you to prove these. We will now take them for granted, as we did with limit laws. But keep in mind that, you can always resort back to the limit definition of the derivative to prove these. So this first one may be known as the power rule. Thank you. And now let's use these derivative laws, if you will, to find the derivative of the following functions. We are asked to differentiate. So now we're moving away from the limit definition of the derivative into just using these laws. So there we have it. We have this function g, and we're asked to find the derivative, g prime. So you see what's happening, right? We have 5 times x. So the derivative of 5 times x, well, first of all, we have a sum. So the derivative of a sum is the sum of the derivatives. So I can differentiate the 5x and differentiate the 4x squared and then add them together. I'm doing this in complete detail for those of you who've never seen derivatives before. I understand that most of you may have, so this is a bit of an overkill, but nonetheless. What is the derivative of 5x? Well, this is 5 times x. 5 is a constant. So this rule here tells you can pull constants out. So this is going to be 5 times the derivative of x. Similarly here, for derivative of 4x squared, 4 is a constant, so you can pull that out. And it's 4 times the derivative of x squared. Now, what is the derivative of x? Well, the derivative of x, or x to the 1, we did it. Derivative of x was 1. You can use this power rule. Derivative of x is 1. Derivative of x squared. Again, you bring the power down. That's 2x to the 1. So we get 5 plus 8x as suggested by a lot of people. Right? We're describing this in complete detail. Of course, as you get more and more experience with this, you'll just be able to read off what the derivative actually is. Let me erase these derivative rules. Same question. Right? The derivative of a sum is the sum of the derivatives. On an exam, you do not have to explain step by step. It should be very clear to the marker what you're doing. Right? So the derivative of a sum is the sum of the derivatives. We're going to differentiate this. And this is 7 over 4 times x squared. 7 over 4 is just a constant. So we'll leave that out. And we'll differentiate the x squared. Right? The derivative of a constant times a function is just that constant times the derivative of the function. Derivative of x squared is 2x. This is minus 3 times x. So the derivative of this is going to be minus 3 times the derivative of x, which is 1. And what's the derivative of 12? Derivative of 12 is? You know what it is. 12 is a constant. Derivative of 12 is 0. Exactly that. So clean that up. 7 over 2x minus 3. Same question, don't let the t fool you. Whether it's t or whether it's x, these are just dummy variables, right? And the derivative is essentially the same, right? Whether you're taking a limit as x goes to 6 or t goes to 6, you know it's the same thing. So same thing with the derivative, right? F prime or the derivative with respect to t, right? T is the variable in use here as opposed to x. So in the same way that the derivative of x cubed is 3x squared, the derivative of t cubed is going to be 3t squared. Right? Con is asking the good question. When we say E, is that Euler's number or a variable? Nobody uses E as a variable. It would be a terrible mistake. E is Euler's number. And so the derivative of E cubed is 0. Thank you. Right? Because E is a constant, 2.71 something something. So E cubed is going to be some number, and the derivative of a number is 0. Exactly that. Absolutely, Pamela. The derivative of any constant is 0. We proved that. That was one of the first derivative rules we proved. R of z is z to the negative 5 minus z to the 1/2. What is the r dz? Right, the derivative of r with respect to z. Here, z is the variable in use. Again, don't let that scare you. It's like an x. It's really x to the negative 5. In fact, you could change it if you wanted to. What is the derivative of z to the negative 5? You bring the power down, and you subtract 1 from the power. Right, that's our rule. Move on to the next one. Bring the power down. Subtract 1 from the power. Right? We're using the rule. The derivative of x to the n is nx to the n minus 1. You bring the power down and you subtract 1 from the power. So minus 5, z to the minus 6, minus 1/2, z to the negative 1/2. Everybody with us? How are we doing? Absolutely. Jacob is asking if we can use either derivative notation for any given function. I will use them interchangeably. They all mean the same thing. Absolutely. So you should be comfortable with all of them because, depending on a question, sometimes it's this notation, sometimes it's that one, or any of the other ones I gave you. Claim, and the book uses uses this as a definition, if you will. The derivative of e to the x is e to the x. Jasmine is asking if in a final answer, would we prefer positives to be exponents, or is this fine? You should be comfortable with all the possibilities. Right? I mean, again, on the final exam, which may be in person, you could have multiple choice questions, and the answer could have been given in any form, including positive exponents, maybe even combining everything into one fraction. So, and you do need to be able to simplify, and we're not going to waste any time simplifying here. But again, on an exam, I would ask you to simplify completely. That being said, this would be acceptable as an answer as far as I'm concerned. But again, if it's multiple choice, be prepared to rewrite this in any form. Yeah, Zuhair is asking me to explain this. I'm not going to right now. Let's take it for granted the derivative of e to the x is e to the x. This certainly suggests the importance of the function e to the x, right? The function e to the x is its own derivative. I don't want to explain it today because, first of all, we are already out of time and I want to do one or two more questions before we leave. But we will come back to this and convince ourselves a bit later. But right now, let's just take it as a definition. Let's take it for granted and apply this to a few questions where it's asking us to take the derivative. So same question, we're asked to find the derivative. Zuhair is asking if x is any real number, won't the derivative be 0? But that could be true for anything, right? If you have x cubed, if x is any real number, won't the derivative be 0, right? If x is 2, then this is a cubed, and isn't the derivative 0? It's true for any function, really, right? The idea is you don't plug in a value of x first and then find the derivative. Rather, you find the derivative first and then plug in a value of x to get the slope of the tangent line. I mean, I understand what you mean, but yeah, it's the same thing for any function. Let's take the derivative here. And before we do that, maybe we should rewrite this as x to the 1/2. So that the derivative, right now we can use that power rule, the derivative of x to the 1/2, bring the 1/2 down, x to the 1/2 minus 1. And this is 2 times e to the x. So I can pull the 2 out and just take the derivative of e to the x. You know that to be one of the derivative rules. And the derivative of e to the x is, by assumption, e to the x. So this is 1/2 x to the negative 1/2 minus 2 e to the x. Let's do one more, and then we'll call it a day. So Jake is asking, e to the x is not a constant. It is not, right? You know the graph of e to the x. This is the graph of e to the x. And what we're saying is that at every point, the slope of the tangent line is the function evaluated at that point. Con is asking an excellent question. Why don't we take the derivative of 2 and the derivative of e to the x separately and multiply them to give 0? And really, you're asking, if you have two functions multiplied together, is the derivative of the product equal to the product of the derivatives? And let's investigate that for a moment. You can think of x squared as x times x. What is the derivative of x squared? You know the derivative of x squared. The derivative of x squared is 2x. What is the derivative of x? We saw that. The derivative of x is 1. So if you differentiate both of these, you don't get the same thing. The derivative of a product is not the product of the derivatives. And now you're looking at this and you're thinking to yourself, well, now we have a power. How do we differentiate this? And it's important that you don't make up your own rules. We don't know how to differentiate that. We can think of this as 2x minus 3 times 2x minus 3. But now this is a product, and we've just seen that the derivative of a product is not the product of the derivatives. So maybe it's something else, we don't know. But can we rewrite this in a form that we're able to deal with? And, just expand, FOIL this, or square the whole thing. This is 4x squared. This times 2. So minus 12x plus 9. Now you have a simple expression that you know how to differentiate. So now you're ready to differentiate. 4 times the derivative of x squared. Derivative of x squared is 2x. We're still using that power rule. Minus 12 times the derivative of x. We saw the derivative of x to be 1. And finally, derivative of 9. Derivative of 9 is 0. So we have 8x minus 12 as our answer, and there you have it. We did not make up any rule, right? And that's very important. So right now, all we're using are those 4 rules. Derivative of a constant is 0. Derivative of that power rule, derivative of x to the n. While Zuhair is suggesting another rule that we have yet to see, we'll be seeing that shortly. Let's don't worry about it for now. Let's concentrate on those 4 derivative rules, while 5 with the derivative of e to the x is e to the x. As Nicholas suggests, you can always factor out 4 here if you wanted to, leaving you with 4 times 2x minus 3. Again, on an exam, I would have accepted this answer, but the answer could have been given in this form as well. That would have been fine. Very good. So practice this stuff. We're moving away from the definition of the derivative. Is the e to the x rule true for every exponential function? No. Only e to the x. Only e to the x, Jonathan, and that will be made clear when we look at the proof for that statement. So similarly for Sophia, the answer is no. If you have a to the x, the derivative of a to the x is not a to the x or pi to the x. Let's hold off on that. We need some more rules in order to figure out what the derivative of this is. But we'll get there. We'll get there probably next week. So something to look forward to. What is the derivative of a to the x in general? All right. Thank you all for coming, folks. You guys have a good weekend. Practice this. Practice these derivative rules, and I will see you on Monday. Have a good one. See you guys next week.